Okay, let's continue. Please take a seat. We have the second plenary lecture coming up. Please take a seat.
Yeah. We are in at 12, so this is the delta.
The delta, yeah. We're within the delta. We're in the delta. So it's an honor for me to present to you Joaquim Martins. So let me just briefly say a few words about him. He's a professor of aerospace engineering at the University of Michigan, author of the textbook Engineering, Design and Optimization, heads the Multidisciplinary Design and Optimization Lab, fellow of the American Institute of Aeronautics and Astronautics, fellow of the Royal Aeronautical Society. Before, he was an associate professor at the University of Toronto, where from 2002 held a Tier 2 Canada Research Chair in Multidisciplinary Design Optimization. He's currently associate editor of the journal Aircraft. More surprisingly, he grew up in the Azores, and to my surprise, and I'm happy to say this, he's also, Håkan, listen, he's also quarter Swedish. Please, Joaquim Martin.
Thank you, Jan, for the introduction. Tak. Okay, so I don't think this community needs to be sold on this, but numerical methods are replacing experiments, right? It's not fully there yet. But if you look, for example, in aircraft design, state-of-the-art A350, there's a reduction in the number of wind tunnel test days by 40%, okay? So this is happening. And in your community, in our community, there's a lot of effort into doing better analysis, doing more complicated flows, multi-phase, unsteady, ships with propellers, great. So a lot of advances in the OpenFOAM community and other CFD communities in the analysis, okay? But I have a question for you. What do you use these analysis for in the end? Most of the time, think about it. Design. Going to design something, right? Engineers are going to design machines, all sorts of airplanes, ships, and so on, okay? How do you do design? Well, one way is to do some kind of design change. But how do you do this design change, right? You're going to run your CFD depending on the type of analysis. It might be a few minutes, it might be hours, it might be days, right? And then at the end, you need to evaluate this design. In this case, I have an airplane here because I like airplanes. And you're going to check the fuel burn, check the structural stresses, and then you're going to do some changes in the design, typically manually, right? You make a few tweaks, rerun, few tweaks, rerun, right? So this is something that's really very time consuming because you might have thousands, millions of different decisions to make, and typically they're done sequentially, okay? What can help here is numerical optimization. So numerical optimization is about automating these design changes. And the idea here, many of you are familiar, I'm sure, you set an objective that you want to maximize or minimize. And then you say, well, these are the set of variables that you can change, right? And you set some constraints, right? Typically, there are a lot of constraints in engineering design. Once you have this problem set up, you press a button, and this whole process should happen automatically, okay? So the utopia is that you're going to have a setup where you press a button, and an airplane comes out, fully designed, ready to go. Does this happen in practice? No. But what happens is that the design optimization process gives you a way of basically exploring the design space more effectively, because every point that it gives you will be optimal for the problem you specified. Now, the chances are that the problem specified is incomplete, or is the somewhat wrong objective function, or the design variables are not enough, or you have forgotten several constraints, okay? But that's okay, you can reformulate the problem, rerun. This gives you a new way to understand your design space a lot faster. Because I tell you, there's nothing better at finding your mistakes than optimization. If you set up the problem incorrectly, it'll exploit that. It'll exploit the weaknesses in your model, okay? It is brutal in that respect, but you'll learn a lot from it, right? So that's what I'm talking about, is design optimization using numerical optimization. Furthermore, the other thing that this is, it's really important is post-optimality studies. Why is that? You need to understand your design, okay? I know from experience, if I show up to Airbus, here's my optimal wing, they ask, well, why is that optimal? Oh, because my great setup here of optimization gave that result. That's not acceptable. You need to understand the design. You need to understand how robust the design is at off-design conditions and so on. So post-optimality studies is something that's really important. Okay, so I do multidisciplinary design optimization, which is about think about multi-physics, okay? Taking multiple physics, multiple disciplines into account. And if you look at MDO, the state of MDO, there's been a lot of progress in that vertical axis in terms of number of disciplines, right? And progress on the horizontal axis in terms of fidelity. And very little progress on the diagonal. This is what I'm trying to advance. Going the diagonal, have multiple disciplines with high enough fidelity. And I would like to say appropriate fidelity, because high fidelity is not always the answer for everything, okay? And that includes a lot of CFD. So that is what I'm going to focus about first, after all this OpenFOAM conference, talk about RANS-based aerodynamic shape optimization first. Now, talking about numerical optimization, there are different types of algorithms. Broadly speaking, there are two classes, gradient-free methods and gradient-based methods. So gradient-based methods use the gradient. This is one of the things I love OpenFOAM for, is there's a gradient symbol in there, right? And we use the gradient of the objective function and constraints to inform the gradient-based optimization. Now, if you look at the gradient-free methods, it's the steep slope. Remember, this is a log-log plot. Okay, so that curve goes up exponentially. And if you use gradient-free methods, you're out of luck for more than a few variables. Just not going to happen. Genetic algorithms, forget it. It's not going to work for more than a few variables. On the other hand, gradient-based methods work really well. They're a lot more sensitive, a lot more finicky, but it's worth learning how to use them, because then you can do thousands of variables. And I'll show you some examples of that. And not only that, you can do multi-physics, multidisciplinary problems. The key here is that difference between the line that says finite differences versus analytic. Going to that analytic line is really the key. And this is what I spend a lot of my research effort with my group on that. Okay, so this led to MacAir, which is a framework for aerodynamic shape optimization. And there are therefore several components there. One is the optimizer, right? There's a geometry parameterization to be able to change the geometry. If you change the geometry, you need to change the mesh. So there's an algorithm to change the mesh automatically. All this needs to be automatically through numerical optimization. And then we have the CFD solver and an adjoint solver. I'll talk about the adjoint solver later. I know a lot of you are familiar with that already. Computes the gradient. That's really important, efficiently. All these are different codes written in Fortran and in this case, multi-Fortran, in the case of OpenFOAM, of course, C++. And they're all wrapped with Python. So I found this was the ideal way to wrap different codes, is using Python. So the whole framework works with Python scripts running the whole thing, right? So the Python wrappers for everything. All of this is open source, by the way, not a GPL license, Apache 2 license, which is less restricted. All right. So on the CFD solvers, I have OpenFOAM, and you'll see there AD flow. I don't suspect you ever heard of this. This is OpenFOAM conference. This is our in-house solver. So we can use either interchangeable because they basically have the same Python interface. So we can either use OpenFOAM or ADFlow, and there's also some efforts to do some of NASA's CFD codes as well, using the same interface seamlessly. So since you know everything about OpenFOAM already, I'm just going to introduce ADFlow really quickly because a lot of the results I'm going to show are based on ADFlow, okay? I'm going to show some OpenFOAM results as well, but keep in mind that because the solver is interchangeable, whatever I'm showing with ADFlow is possible with OpenFOAM. So you'll see that. Okay, so ADFlow, first of all, is a structure overset. So that's it's really an issue with making the mesh because it's a structured mesh. So there's a lot of effort that needs to go into that. Although once we have a nice structure mesh, that works really fast, right? But the upfront cost is expensive. It's parallel and solves the Rand's equations. We have an approach that we call the approximate Newton-Krylov method that's really robust, so converges very off-design cases. And we got the Sparma's turbulence model. And one of the most important features here is a full discrete adjoint for the whole thing, all with analytic derivatives. Okay, so a fully analytic, no finite differences or anything like that. So it's really efficient. As I mentioned, OpenFOAM can be used interchangeably with this using the same interface. Overall, OpenFOAM, we use simple foam mostly because the pressure-based solver really is good for low-speed flows. ADFlow, not so much because it's a compressible solver, but it's better for the type of aircraft we do, transonic transport aircraft. Now, ADFlow is faster in general, but with OpenFOAM, we can still do optimization. So what are the characteristics of a CFD solver that you want to integrate in a multidisciplinary design environment, right? So first is the solution failure handling. So if the solution fails, you cannot stop the optimization, okay? For that, you need an optimizer that gives you the option for a fail flag. What the optimizer will do is, okay, you cannot do that point, let me backtrack, try this one, and so on, right? And usually this works, although it's very intensive. Even better if your solver is robust enough to at least converge a solution, even though it's not physical, if it still gives you the right trends, that's okay. Solution restart is really important because you want to do drag polars, parameter sweeps, and so on. Also a robust startup. So again, I already mentioned being able to start from anything. And being really efficient to converge in all solution phases. And one very important feature here is direct memory access through an API, right? So you need to be able, no file IO in the middle. You have multiple codes coupling, you're running this over and over again, optimization. You cannot afford to have file IO, that'll kill your performance, right? So everything we've done is through Python APIs with direct memory access. And that's been really the key for everything. And finally, the most important feature is efficient array computation. So we can do our gradient-based optimization efficiently. Okay, so just to give you a teaser here on what we can do, we're starting with a circle, okay? This is a CFD solution of the circle. The solution is not physical, okay, because you got separated flow in the back. But our approximate Newton-Krylov solver still solved it anyway. It's unsteady, but it made it steady artificially. But it got the trends correctly because there's a lot of drag and no lift. Exactly the opposite of what we want, right? So on optimization, what we're going to ask is maximize or minimize the drag and give us a certain lift. We have a lift constraint, okay? And this is full automatical. So watch what happens. Immediately figures out you can flatten this shape and reduce the drag drastically. It gets a bit confused which one's the leading edge, which one is the trailing edge. Eventually figures out rounding the leading edge, the flow is coming from left to right, and sharpening the trailing edge is the way to go. So those are the characteristics of an airfoil. And not only that, because this is compressible flow, we're at 70% of the speed of sound, okay? It flattens the top to reduce the shock wave drag, okay? This is a characteristic. All the airplanes you flew over here, unless they were propeller, have this supercritical airfoil. Took NASA a decade to come up with this. This optimizer came up with it in a couple of hours, okay? Just a couple of decades late, but it reinvented the supercritical airfoil. One of the things I want to highlight is some of the intermediate points that you didn't see are these crazy designs that the actual designer would never ask for in CFD. But the optimizer will try crazy things because it's trying to explore the design space, right? But the key here is that our solver did converge this, even though the physics is wrong because this will be unsteady. It got the trends correctly. And the trends say that flattening the shape, reducing those peaks, and sharpening the trailing edge is the way to go to reduce drag. So as long as that's the case, it doesn't matter if intermediate points in optimization get the physics wrong. It's the trends that matter. So I have this dream of taking a sphere, putting in my code, pressing a button, and out comes airplane. So halfway there, got the circle to airfoil, but I'm not quite there in terms of going from a sphere to an airplane in 3D. But this is the closest we could get. So a student of mine figured this out, how to do a body that traps on any arbitrary shape. In this case, the arbitrary shape is a human, right? It's complex enough. And watch what happens. We take a simple axisymmetric shape and it basically shrink wraps, figures out reduce the area, but don't separate the flow. And it basically comes up with this shape. It looks like record-breaking recumbent bike. Okay, so now that the teaser is over, I'm going to explain a bit more how we do this. The next, we have geometry parameterization. So this is a module called PyGeo. But we can also, again, because it is modular, we can also use other ways of parameterizing the geometry. In this case, OpenVSP also works. Okay, the way PyGeo works is using free-form deformations or FFDs. Basically, you enclose the whole airplane in a volume, a free-form deformation volume, and you change the points on the surface of that volume, and then everything inside gets changed. So here, for example, we can change airfoil shape, shown now, the span of the wing. We can also change the sweep and change the twist distribution of the wing, which is a really important variable in aircraft design. And finally, you can rotate the tail as well to trim the airplane. Okay, now that we have a way to change the geometry, we need a way to change the mesh. We first change the surface mesh and then the volume mesh. And here you can see the geometry and mesh working together. So we need this capability to be fully automatic. We don't want to redo the mesh manually, right? Or regenerate the mesh. We basically perturb the existing mesh, okay, in a smooth way. It needs to be smooth because of the gradient approach. Here's a 3D example. Basically, we take this wing, and at every step here, we have a different CFD solution on it. So this loop was done automatically. This is not optimization, it's just really testing the geometry and the deformation here. All right. So what about optimization? Well, I already mentioned we use the gradient-based optimizer. And the underlying optimizer we use is called SNOpt. And we have developed a wrapper that wraps that as well as many other optimizers. So again, the idea of using a common interface for multiple codes. So you only need to learn the interface and then you can change whatever you have underneath. And again, this is all open source. So that's PyOSparse. Okay, the all-important derivative computation, so computing the gradients. We use the Adjoint method, okay? So in my book, I like to explain the big picture first. The big picture is if you have a black box and you have inputs X and outputs F, and you want to find the derivatives of F, which could be a vector, with respect to another vector, which is X. That's a Jacobian, right? How do you do that? Well, if you have a black box, you have no access to what's inside, you are limited to using finite differences. You perturb the input, have a new output, subtract with the reference, divide by the step, and you get your difference, all right? Forward difference, backward difference, whatever you like. Another way to do it is if you code this complex, you can use a complex step method. If you never heard of the complex step method, I encourage you to look it up. It's a very neat alternative to finite difference. It's not subject to subtract cancellation, so it's can be numerically exact if you do it properly. Okay. The downside of these methods is that the cost of computing the gradient is proportional to the number of components of X. All right. So you saw previously, I have hundreds of design variables, all these twists, all these points moving around, right? So it's not feasible to perturb each one, recompute the CFD, do the difference for 1,000 times. It's just not possible, okay? So we need to be smarter. How do we get smarter? Well, we need to look inside the box, okay? So at the first stage, you could open the box and understand what equations are being solved. So you have a solver, they're solving a set of residual equations, right? That's the typical. You have state variables u, and then you have a function that's a direct function of u, an explicit function of u. And if you have that structure, right, you can apply what we call analytic implicit methods. That includes the adjoint method. And I'll explain that in more detail in a bit, okay? The other option is that, yes, you open the box, but now you're not looking at the equations level, right? This more abstract level. You're looking at actual lines of code. Once you look at actual lines of code, you can do algorithmic differentiation, also called automatic differentiation. That means differentiating every line of code. And this can be in forward mode or reverse mode. I won't get into that, but I will just say there's an analogy between reverse mode and adjoint mode, and I explained this in the book. Okay, quick introduction to the adjoint method. So we have our design variable vector x coming in, and this affects both the solver and the function you're computing directly. So we need these two paths. So we have two terms there for the total derivative f with respect to x. The first indicates the direct path from x to f, and the second one, the indirect path that goes through the solver. That indirect path is expensive because it involves solution of the governing equations, right? So that's that term du dx. That term du dx depends on the solution of the governing equation. That's why it's a total derivative. The partial derivatives, they're cheap to compute, even if you do them by finite differences, because they don't involve resolving. Du dx is expensive, but we have a smart way to compute du dx. That's looking at the variation in the residuals. If you look at the variation of the residuals, it needs to be 0. So if you change x or u, a change in x must be compensated by a change in u and vice versa for the residuals to remain physically feasible. So r equals 0. And that's what that second equation tells you. And if you reorder that, you get a linear system. With that linear system, you can get du dx, okay? So the states with respect to your design variables. Then you can replace that in the equation above to get the total derivative df dx, which is the one you want, all right? Okay, that's the direct method. And that's shown in the bottom. If you take that red big matrix Jacobian, solve with the rdx on the right, that's a direct method. But now that we've written this whole equation, we can see there's another way of doing it. And that is to take that matrix and solve it with the right-hand side, the FDU instead. You need to transpose everything. If you do that, you get the adjoint method. And if you do that, the cost is proportional to the number of functions, but independent of the number of design variables, x. Okay, the direct method I explained before, still proportional, the cost is still proportional to the number of x's. Okay, the adjoint is independent of the number of x's. And that's the whole key for the adjoint method, right? Because now you can have thousands of variables and a few functions. If you have a few functions, many variables, adjoint works wonderfully. And that's why it's so useful in aerodynamic optimization and other MDO problems where you have a few functions of interest, a lot of design variables. And that's been the key for all our work. Okay, now we can decompose the implementation of the adjoint. So the adjoint, of course, the downside is implementation. It takes a lot of implementation effort, okay? There have been whole PhDs on just implementing adjoints. So we've worked a lot towards simplifying the implementation. And what we did in this paper referred to here is that we can separate the implementation into two parts. One is solver agnostic and the other one is solver specific, okay? For OpenFOAM in particular, we developed this approach. It unfortunately has to use some finite differences in there. I mentioned finite differences can be problematic, but it still works well enough. And for the finite differences, I mentioned these are really inefficient and can be inaccurate, but we have a way to reduce this cost, right, by using graph coloring. I'll show more details in a second. Then you have the step 3 there, that's doing automatic differentiation. So one of the things we do is combine automatic or algorithmic differentiation with the adjoint. So to compute the partials on the adjoint, we use algorithmic differentiation. So there's a hybrid method between adjoint and AD, or algorithmic differentiation. So that's step 3. And then for step 4, we have used GMRes. So that's a matrix-free solver to solve for the adjoint equations themselves. And that saves a lot of, in terms of memory, and also increase the speed and the convergence as well. For the coloring, what we develop is a heuristic coloring algorithm, right? And that basically improves the speed by 3 orders of magnitude in general, and makes it possible to do 100 million, up to 1,000 million cells, right? Because we need to store the matrix vector products in memory. Now, this kind of system is usually pretty ill-conditioned. Okay, so we use nested preconditioning here. So we use an outer additive Schwartz preconditioning, and then on the inside loop use ILU. Okay, and this makes it really fast. It's parallel and robust convergence. Okay, so all this talk about the adjoint. I once had a colleague at NASA said, "Oh, you come to give a talk at NASA. Don't mention the adjoint." Why? Why can't I mention? Well, you know, my managers, you mention adjoint, their eyes glaze over and they think it's too complicated, they don't understand it. Okay. But I'm going to tell you, don't be afraid. Okay. Let's do some adjoints. It's nothing to be afraid of. Because once you realize the power of the adjoint, you're not going to want anything else for optimization, right? So in my group, yes, we are addicted to adjoints. And I know for those of you who are not familiar with adjoint methods, I know it's a lot to understand just in a couple of slides. It's not possible in my experience, but I offer you my book. The full PDF is available for free. And chapter 6 is all about computing gradients. Section 6.7 is about adjoint methods, right? And there's some more advanced concepts in there as well. So the approach with the adjoint implementation in OpenFOAM, I mentioned before, is also extensible. So my colleague Ping He from Iowa State University, while he was in my group, he developed this general way so that is a template that you can apply to different OpenFOAM solvers to do an adjoint. So if you have a solver for which there's no adjoint in OpenFOAM that you're interested, please contact me or Ping. I'll be able to help with that. All right. So the whole idea is DAFOAM is this framework that can do it automatically. And thanks to that, we solved some aerothermal optimization problems. So this is a cooling passage, and there's typically a trade between the aerodynamic performance, so the pressure drop versus the thermal transfer. And you can see on the left, there's a simultaneous improvement in both measures by changing the shape. On the right, the shape is fixed, but we're changing the ribs, the orientation of the ribs there, right? So these optimizations were done fully automatically, all right? We also did some turbine optimization. This is an aerodynamic optimization, a structural optimization, not coupled, just done separately here, okay? Now, those of you familiar with the adjoint in OpenFOAM are going to ask me, what about the continuous adjoint? Okay, so you recognize that the derivation I made was for a discrete adjoint. So the idea there is you take the discretized equations, they're already in matrix form, they're already written in residuals, right? And you differentiate that, and you get the adjoint equations already discretized, okay? The continuous approach is very different. Continuous approach takes the original PDEs, differentiates that by hand, right? And then you can use some very smart tricks to increase the speed, reduce the memory. Okay, and then you discretize those continuous differentiated equations, right? So it requires quite a bit more mathematical insight and effort, right? So it's not as straightforward, but it can be more efficient. Now, one key thing for optimization is that the continuous adjoint is not consistent. The final result in the gradient is not consistent with the discretized result on the function, because they're different discretizations. They tend to each other in the limits, right? So that, in other words, the gradient is not going to correspond to the gradient of the function being computed because of all the numerical errors. And that does affect optimization, even if the errors are small. In that case, the continuous adjoint is a lot better, or the discrete adjoint is a lot better for that. All right, so let's look at a few more applications. One of the things we've done is create a benchmark for aerodynamic optimization. And this is one of the first. So this is RANS-based optimization of an airliner wing. So going at Mach 0.85, so 85% the speed of sound. So definitely compressible with shocks and so on. And you can see here that there's some shocks, and our optimization is able to completely eliminate the shock because we're asking it to reduce the drag or minimize the drag at one single flight condition. And it does that by removing the shock, reducing viscous pressure drag, and so on. And you can see how the pressure contour lines are nicely parallel. So that's a great feature. You got elliptical lift distribution. So it's really the perfect wing for that one condition, not very robust though. But that's okay. We can do multi-point optimization as well. There's some benchmarks on that. I won't show all the results. But this has been really a way to make this routine, this kind of optimization of wing shape optimization routine. And this takes about 6 hours on 128 cores. All right, so this is maybe 200 design iterations, okay, all done automatically. Okay, so this is great, starting from a wing that's already well designed. This was a benchmark created, or the original shape was created by Boeing and NASA. We make it better. But what about starting from something really bad? So I asked my student, what is the crappiest wing you can start with and still get this optimum, the same optimum, right? And my student showed up with this, right? I thought he was joking, but actually not. If you look at the optimization, it actually works and we get the same result. So again, the physics of the initial analysis is wrong, but the trends are correct, and that's what matters. And in the end, once you smooth that shape, which it tends to do, then you get the very accurate answer on the CFD side. All right. Okay, so this was done with with AD-Flow because it's a compressible solver. On lower speed, OpenFOAM is usually better, and this is a lower speed wing, so you see no sweep, and you can see we do a single point versus multi-point optimization. If you look at the multi-point optimization in red, is a lot more realistic, consider multiple flight conditions. So it's not just tuned for one condition. It's got a rounder leading edge, more like a real airplane, a wing, okay? And you can see the difference in the drag there. Also, full configuration is also possible with OpenFOAM. In this case, over 200 design variables, over 700 constraints, reducing the drag by 3.6. This is the common research model. Again, the same model that NASA and Boeing developed that we've worked on. And you can see changing the shape of the wing, changing the twist of the wing to reduce the drag. Now, one of the challenges is to do transient problems. So, and we can do that OpenFOAM to a better level than we can do with my other solver, the AD-Flow. So here we're optimizing an airfoil to reduce the mean drag. Then 3D as well. So in our field now, there's a big push for urban air mobility, which a lot of propellers, interaction with wings and so on is really important. And we can reduce the drag, average drag of that unsteady computation as well. It requires an unsteady adjoint, which requires a lot of memory, but it does work. It is very expensive though. Other work we've done beyond aerospace engineering, because we saw other applications, the OpenFOAM work was actually sponsored by Ford Motor Company to develop the first adjoint for OpenFOAM that we did, the discrete one. And you can see there, which changing the backside of the car there to reduce the drag, and that worked really well. Also, you mentioned ships earlier, also like ships and sailing boats. And in this case, we're doing what I call hydropropulsive optimization. So we're changing the propeller parameters as well as the hull, the backside of the hull, simultaneously to reduce the drag. Okay, and that's a common theme in MDO. Consider as many disciplines as possible simultaneously. Consider as many design variables simultaneously as possible, because there are interactions between the disciplines, There are interactions between the variables that get you a better result than if you did things in sequence. Okay, so in this case, if you design the propeller first, then optimize the whole shape, and even if you went back and forth, you wouldn't get the same result as doing everything simultaneously, right? So showing a lot of numerics here, but a few results have been validated experimentally. In this case, this Ahmed body that where the angle was optimized, and we got experimental verification there. All right, so far I'm talking about a lot of fluid dynamics, only fluid dynamics, but there's more than that, right? We need to consider in wings, for example, the flexibility. So then we need to couple the structure with aerodynamics to find the flying shape. Not only that, at different flight conditions, you got different shapes. So how do you consider that? Well, that's where we need to consider the coupled effect. And for that, we need an optimization approach that takes that into account. At each flight condition computes the new position of the wing. Now, remember the gradients, the adjoint. Now we're going to do the coupled adjoint. Okay, that means we have an adjoint on the fluid solver, we have an adjoint on the structural solver, and then you have an adjoint of the coupling. What that means, you see on the bottom right, is that you get a Jacobian, a block Jacobian of matrices. And now you have to have derivatives of residuals of the structures with respect to the flow variables, and residuals of the CFD solver with respect to structural variables. Okay, so that's a huge coupled matrix, right? Seems kind of unmanageable, but it is manageable, and we showed it. And we extended this framework, Mach, to do coupled solution of aerodynamics and structures with a coupled adjoint. So again, the key here is the coupled adjoint approach, okay? To make that scalable, to make that accurate enough for a gradient-based optimization. But it did work, and you can see here the scalability of doing finite differences versus doing the adjoint method. So with finite differences, is a linear variation there, but it's very steep. You cannot handle more than a few variables. Whereas with the adjoint, you can do thousands. The slope is practically flat, right? That's the key of the adjoint, and in this case, the coupled adjoint. So now we can actually do aerostructural optimization. What does that mean? First, we have a model of the structure on the left, a model of the CFD on the right. The two are coupled so that you get the flying shape. Second, we're going to consider all variables. We have structural sizing on the left and structural arrangement, right? And on the right, we have shape, but this shape is not just the aero shape because it's linked to the internal structure. So you can see the changes there on the airfoil shapes, change the structure on the left as well, okay? And you're gonna see changes in sweep, span, chord variation, and they're all linked there. And we're considering all these variables, almost 1,000 in our optimization that I'm gonna show you here. And this is the optimization. So here is an airliner. This is typical of a 777, Boeing 777 size wide body airplane. And we're optimizing all those variables. And I'm gonna solve two problems here. Same variables, same constraints. The only difference is the objective function. On the left, we're minimizing takeoff weight. So this includes fuel, payload, structure, everything. On the right, we're just minimizing fuel. And you see the difference. When you minimize fuel, you get a longer wing. Why is that? Because we want to reduce drag at all costs. If that means a heavier wing and a heavier airplane, so be it. But we burn less fuel. This seems paradoxical. We get a heavier airplane that burns less fuel. But that's the way it works. It's an aerostructural trade-off. On the left, we get a lighter airplane, but it burns more fuel. Okay? So we can do these trades and do intermediate points as well. And you can see how the structure was sized, the shape of the wing, and so on. All right. So, and by the way, this runs about 2 days with 1,000 cores. Okay? Still not bad. It's with AD Flow, not OpenFOAM. But again, this can also be used with OpenFOAM. We've used this for several studies of new technologies. In this case, a NASA-sponsored project to do toe-steer composites. Our high aspect ratio wing actually got a third scale built by Aurora Flight Sciences. You can see the tow path of this building with the automatic fiber placement machine. On the right, you can see the wing after it was being built. That got tested at NASA Armstrong. And after the testing, they had didn't break, by the way. That's great news. After testing, they had no use for it, so we brought it into University of Michigan. It's now in our Aero building on display there. Okay, so let me show you a few more examples, multidisciplinary examples of OpenFOAM. The credit for all these goes to Professor Pinhead from Iowa State University. So we're taking the same common research model, doing a drag reduction there. Also the turbine problems that I showed, both fluid and structure, in this case separate. And you can see the FFD showing the changes in the structure there on the shape. And these are the cooling passages I showed before it showed the picture of the actual cooling patches. These are located in turbines, in gas turbines. So the airplanes we fly with turbofans have those in there, and so on. Another application has been wind energy. So wind turbines are like big wings rotating around, okay? A bit like a rotorcraft. Again, we're able to do the structural, the structural coupling with the aerodynamics, can do a structural sizing, and then we can simultaneously optimize the structural sizing so it doesn't break and the aero shape, okay? And by the way, I didn't mention before in that airplane, there are structural constraints for several maneuver conditions that say basically that the wing shall not break off, okay? That's basically the constraint. We've also applied that to hydrofoils. Very interesting. Now naval engineers have rediscovered or more emphasis on hydrofoils. They're basically wings underwater. So we can actually apply these tools as well. Now we have issues with cavitation, so we can set cavitation constraints. So in this case, we have a T-foil. We're simultaneously constraining cavitation and separation while minimizing drag and constraining the stresses, because this is an aerostructural, I should say, hydrostructural solution. All right. So, yeah, and the application, obviously, if you are into sailing, you know, the ocean race just finished last week here. They're not using hydrofoils, but America's Cup is now totally dependent on hydrofoils. And it's an amazing configuration they have here, the ACA75, and really very interesting problems with hydrofoil optimization. All right, now transition to something else, which is, I've been talking about coupling aero and structures, but we want more. We want all disciplines, all possible disciplines, multi-physics, anything you can think of, okay? That's the ambition. How can we achieve that? I showed you that the Jacobian got very complicated, even with 2 disciplines. You have 4 sub-blocks, 3 disciplines, 9 blocks in your Jacobian, okay? Well, the way we achieved it, while going back to the drawing board and trying to generalize derivative computation. And what we came up with was an equation that unifies all different ways of doing derivatives. I actually thought at the time this was pretty useless. It was more of an intellectual curiosity. I wanted one equation to show everything, right? But in the end, it turned out quite useful, and it ended up on this modular analysis unified derivatives approach, which is an approach that takes these partials and total derivatives and can organize them in a hierarchy. So now you can have nested systems. You can have systems of multiple disciplines, multiple components. It's very flexible. And we showed that this worked. And once we showed this worked well, we collaborate with NASA to implement in their open source framework called OpenMDO, which is a framework for multidisciplinary analysis and optimization, okay? By the way, if I ever say OpenMDO instead of OpenFOAM, is because I'm more used to saying OpenMDO. Right, so the main idea with OpenMDO now, especially with this new approach implemented, is that it's going to help you couple different systems and solve the coupled system efficiently, because we use Newton-type methods and some advanced fixed point iteration there, right? So the methods are implemented to do that. Furthermore, it's all geared towards computing coupled derivatives with a coupled adjoint method. So if you implement all these partial derivatives, it organizes everything, puts everything together, and computes the coupled derivatives automatically, all right? So as an example here, you can see how this hierarchical system organized. You can see the connections between the different components. Above, you have a feed forward. Below, you have feedback. So the system is coupled. You can think of this like a sparsity matrix for a multidisciplinary system. And you can see the expand and the hierarchy. You can see how many variables and components are involved. So there have been many OpenMDAO applications in the last few years. There's a link there to all the papers we've written that use OpenMDAO. And there's very varied applications, including satellite optimization, topology optimization, and so on. Now, OpenMDAO in that form was not enough for CFD-based optimizations or even any structural finite element code, because it was not enough to handle high fidelity codes, so PDE solutions. And so in an effort with NASA, again, we developed Envis. This is a framework specifically to handle PDE-based solvers, right? And we're now able to do aerodynamic structures, and we're basically closing the loop. Remember, I showed you what we developed in terms of aero and structures. That was a very long development time, very custom code for that aero and structures problem, okay? What we did with Envis was to generalize that, generalize the coupled adjoint, generalize the coupled solution, and now use any code in a modular way for any discipline, okay? So if you're interested in that, I encourage you to look at Envis. OpenFOAM is coupled in there, all right? With Envis, we're able to solve air-propulsive integration problems like this Star KBL configuration from NASA, which has electric propulsor in the tail to ingest the boundary layer and increase the air-propulsive efficiency. And here we are optimizing the shape of that nacelle and the tail cone simultaneously with the propulsor parameters. Not just that, we actually evolved to turbofans. So turbofans, you have a thermodynamic cycle happening there. You got the combustion that we don't model right now, but we have a thermodynamic cycle code coupled to the CFD. And all these are being optimized simultaneously and getting a feasible and optimal result there. A really tricky, very nonlinear coupling here and challenging to solve. We just recently succeeded in that. All right. Now, this is an example from my PhD student, Bernardo. Bernardo is there. Raise your hand. He's going to present this afternoon a workshop on, or a tutorial on DAFOAM, the OpenFOAM Adjoint. And he solved this extremely challenging problem. This first time we actually combined 3 disciplines: aerodynamics, acoustics, and structures. Okay. Again, thanks to Envis, it wouldn't be possible otherwise. It would have taken too much time. He'll talk more about it in his presentation also on Wednesday morning. He'll present this work. So there have been other applications of Envis. So not only just this problem I talked about, also with aerothermal design. So combining CFD with the heat conjugate transfer, and also the aerostructural problem, and also problems involving flutter. So that's more of a transient problem there. So many applications there. So in a nutshell here, what a message I want to put across is that we enabled MDO, multidisciplinary design optimization, in OpenFOAM, okay? Made this a reality and made it practical enough that you can use it. And the key is really combining gradient-based optimization, gradient-based numerical optimization with efficient computation of gradients using the Adjoint method. That's the key. And there's no other hope to handle larger number of design variables, right? Also with DAFOAM, we implement the adjoint, the discrete adjoint. And this will facilitate other adjoints, as I mentioned before. So yeah, don't forget the DAFOAM demonstration today. It's at 2:40 in Aula Benvenuto. Okay, so I have a lot of demonstrations, very large scale demonstrations with up to thousands of variables. And now with Envis, we're really opening the door to more disciplinary problems. So I want to close with this kind of triangle of impact here. It's really important to develop theory, but not in a vacuum, all right? It needs to be informed. And I like to have things open. So that's why the book, which has a lot of the theory that's necessary to do what we did, I made it free. I get a lot of inquiries from all around the world about MDO and being in my group, I cannot take everybody. And I know a lot of people cannot afford a $100 book. So the full PDF is free if anybody is interested. And also then implementation is often underestimated. And it's very important because without a decent implementation, you cannot show industry and more practical people that this is feasible. You can actually do this in finite time. And implementation is sophisticated enough to handle practical problems. So this is the work that I've done with industry, we have done with industry, really helps is to inform that theory and the implementation. And this has been really humbling to go to industry and show results and get picked at the details and sometimes big things. So you learn from that process and you go around until you can have some impact there. So again, we have free book, we have open source software. So all I can tell you is go forth and optimize. Thank you.
Thank you very much, Joachim. At this point, do we have any questions?
Hi, thank you very much for that. So you mentioned automatic differentiation, and you also mentioned complex number derivative calculation. Is that practically the same thing, or is it or is there a difference?
So complex step derivative approximation is equivalent to forward mode automatic differentiation with overloading. Yes. But not the reverse mode, which is usually the more interesting one.
Thank you. I have a different question this time, which bothered me for a long time. Okay, so when you're doing continuous adjoint, one of the problems that I have is that my forward problem needs to be fully converged, which it never is. But with discrete adjoint, you get much more consistency between the forward problem and the derivative problem. Yep. So are the values that you get from the discrete adjoint correct, even if your forward problem is not converging properly?
In a short answer, no. They're as incorrect as the governing equations, if not more incorrect, right? But at least they're consistent. So even if they're incorrect, if you optimization can keep going, that's okay. So as I mentioned, intermediate results don't matter as much as long as they point in the right direction, right? And with gradient-based optimization, you can actually show if it's pointing in the 180-degree sector that has feasible descent, well, actually the cone that has feasible cone of descent, it's okay, at least to begin with. At the end, if you want to converge really well, then you better have good gradients. And this has been a problem with our OpenFOAM work, where there is unsteadiness, like the car, there's unsteadiness behind the tires and so on, where the flow didn't converge very well. The adjoint converges okay, but it's not the correct value. And then at the very end, we don't get a very precise optimal answer. Yeah. Other questions? There's somebody there and somebody there.
Hello, thank you very much for your very comprehensive talk. I have a question about the gradient descent. So when you make a gradient descent step and things don't work, what do you do then?
When you make the gradients, what?
When you make a gradient descent step and then, for example, the simulation doesn't work anymore, what do you do then?
Oh yeah, so so that depends on the optimizer, but the optimizer we use does backtracking. So in gradient-based optimization, there's a line search, okay? Chapter 4 in my book, it's all in there. And this is explained there. So when you have a fail flag, it'll do a backtracking. So it'll backtrack from the line. So the step went too far into a region where it's not solvable. It steps back until it's solvable again. Now, that's kind of a last resort thing. It's not ideal because that's all the optimizer can do, is to backtrack. Eventually, you can prove that, yeah, it will get the point, because if you're in a point that converges, if they take a very small step, it should converge as well. right? But it might be very small. And then in the next iteration, hopefully it will change direction and do a nice search in the other direction, right? So, but you like to avoid that as much as possible. So it's always good if you can converge. Right. I think there was another question back there.
Hello. Hi, Professor. Thank you for your presentation. I have a question from two takes in your presentation. So in the start, you said non-gradient based approaches like genetic algorithms have a lot of problems because they have a lot of underlying variables that affect the optimization.
Right.
And you mentioned a calculation where it took 100 cores and I think 2 days to finish the whole optimization, the calculation process. So this is more of an opinion question. What do you think about other forms of data-driven modeling, like deep learning, that could be utilized for optimizing that?
Right. So I've thought about that a lot. I get that question a lot too. If you think about optimization, the type of optimization I'm doing, right? You want to achieve the optimal result with a minimum number of evaluations because they are expensive, right? And in this case, we're talking about a couple of hundred, right? What is data-driven modeling? And what does the AI do? It processes a lot of data, right? We don't have a lot of data, okay? So that's my answer. So now there are applications of machine learning, and we do use it. You can search through our papers for some surrogate modeling. There's also people who do physics-informed machine learning, which also looks promising and so on. But for as an optimizer, machine learning is not efficient at all for these problems.
Thank you.
Yep. I think he was there next.
Yeah, thanks for the presentation. Very interesting. Ivan Spiss or Leonardo Company. My question is more general. You talk beginning of design because these tools, of course, are used by design. But when I go to the industry, you know, for design process is very important the certification. What about certification? This type of very powerful tool. I'm not. This is more, let's say, this the issue.
So what I would say to that is, I'm not an expert in certification, but you can take an optimized result, right? You can take an optimized result and then try to certify that, right? Then if there's a problem, come and talk to me. But basically, some of the solvers are not have not been tested that thoroughly, right? But you can do that after the fact. Does that make sense? Yeah. Right. So yeah. So that's a challenge. So can you take existing tools and do this? You can, but they won't be very efficient because sometimes you'll have a black box and you cannot open the box. That's the issue. You need to be able to open the box to make things efficient. So OpenFOAM is great because it's a totally open box. It's very complicated, right? It's a bit of a monster, but yeah, it's open. Yeah.
So if you have a fully unsteady flow, and unsteadiness is important, typically in a joint optimization, you need to store all your history. Now, is there a model reduction strategy that you have used that allows us to not to store the whole history or to do something to render the optimization feasible?
Yeah, so we haven't done a lot of work on it. We've tried a few things. I showed you some unsteady optimization, not model reduction, although that's an idea. We've used checkpointing to do that kind of thing. But yeah, I don't have any better ideas than the state of the art right now for that. Yeah. Over there. Huh? Benito.
I think we need to interrupt now. I'm very sorry. Maybe we can continue the questions during lunch because we're a little bit late. We have a lunch break now until 1:30. Lunch is served on the 4th floor where you did the registration. So you basically come up to the 4th floor. Instead of going to the registration, go a little bit to the left, and then there's the courtyard. And food is in the shadow. It is hot, but you can find a place in the shadow. So that's for that. But before of course, I want to give you this, again, the book.
Thank you very much.
Thank you again, Joaquim, and enjoy lunch. And please drink a lot, it's hot.